Hello, welcome to another episode of Math with Haas. You're watching Precalculus Season 1, Episode 12. We're continuing where we left off with the last video, where we looked at the relative growth rate and the doubling time growth models for populations. Now, what we're going to do today is talk about radioactive decay. So, if we consider the exponential growth doubling time model, we had p is equal to p naught times 2 to the t over d. For radioactive decay, we want to think about we have some amount of radioactive stuff like uranium, and if we have like 100 grams of it, there's going to be a time when that will decrease by half. You'll have half that amount, and that is the idea of a half-life. So half-life is the time it takes for a sample to be half of its original size. So we could say for a sample to decrease by half. So then we're going to denote this with a h. Okay, so we'll just say this will equal h. So when we talked about the doubling time model, we had a 2 to the t. Now we want to think about, since we're thinking how long it takes for something to be cut in half, we want to think about something like this, a half to the t. So if we think about a half to the t, well, this is going to be the same thing as 2 to the negative t. Because if we recall, if we have x to the negative 1, that's the same thing as 1 over x. So our radioactive decay, we can initially think of it as a mass is equal to an initial amount times 2 to the negative t over h. So m would be our mass at time t. M naught would be our initial mass, how much of the radioactive substance are we starting with. H is our half-life. So we'll type that out. So m equal mass m naught would equal our initial mass, initial sample size, and then we said h again. Yeah, we can type that out too. Let's X out that. We said h was equal to half-life. Alright. So when we could, so this would be a model based off half-life, but suppose we want to think of it in terms of a relative decay rate. So we saw for the relative growth rate, we had something like p is equal to p naught e to the rt. For the relative decay rate, we want to think a negative in here. So r is now going to be think of it as a negative r now. And with the inclusion of that negative, that will guarantee that our sample size will be decreasing. So we could replace these with m's if we want. So we could think of the mass is equal to initial mass e to the negative rt. But it's pretty much the same equation as before. Now, what is the relationship between r and h? And we can do our derivation like what we did last time, define the relationship between doubling time and the relative growth rate. We can set m equal to the initial mass over 2, and then this will have to equal our equation and we'll go ahead and solve it now. So we'll divide out the m naught, leaving us with a half is equal to e to negative rt. And then we can take the natural log of that. So natural log of a half is equal to natural log of e to negative rt. Now on the right side, natural log of e to the x is just x. So we have natural log of 1/2 is equal to negative rt. Now on the right side, we have a natural log of two things divided by each other, and if we call the law of logs, we can break it up into subtraction. So this will precisely be natural log of 1 minus natural log of 2 is equal to negative rt. And now we can include another property we talked about. I should have put this one in blue. We'll just underline it since I forgot. But the natural log of 1, or the log of any base with a 1 plugged in, is just 0. So then this thing simplifies to negative natural log 2 is equal to negative rt. And now we can multiply by negative 1, get rid of the negative, so natural log 2 is equal to rt, or natural log of 2 is equal to, well, natural log of 2 over t is equal to r. Now, since we had said that we are looking for we are interested in doubling time or half-life, in this case, t is equal to h, because we were assuming that half of the mass was gone by this particular t value. So this t is actually our h value. So this tells us that the natural log of 2 over our half-life is going to equal our relative decay rate. So that's the relationship between our two models. It looks very similar. The only difference now is that we're going to have a negative in our equation. So let's go ahead and look at an example now. So example, I'll type this out also. So, oops, I don't know what I just typed. Alright. Polonium, let's move the cursor. Polonium 210 has a half-life of 140 days. Suppose you have a sample of about 500 mil. Let's say 500 grams. It's a lot of polonium. Find the remaining mass after about 2 years. 2. How long will it take for the sample to decay to 100 grams? And 3. I think that would be good. We'll just do that. Alright. So, let's zoom in a little bit. Alright, so polonium 210 has a half-life of 140 days. This information right here tells us that H is going to equal 140 days. Now, next we see that we have a sample of 500 grams. So this tells us that the initial mass is equal to 500 grams. So now we can look at question 1. So for 1 here, we see here, we're asked to find the remaining mass after 2 years. So find the remaining mass. We'll use pink here. So this means we want to know what does m equal, and we are told that we're told that time is 2 years. So this is t is equal to 2 years. So what we need to pay attention to is the first, we got this fact here. Let's go ahead and pick up blue. So we have units in years and units in days. So it doesn't matter which unit you use, but you have to be consistent. You cannot use both days and years. You have to use one or the other, or your math will come out funky, and we don't like funky math. So that's the first thing. I think I will just work in days, make it easier. That way I don't have to convert half-life to days. And then so in this case, then we want to think about 2 times 365, because there's 365 days in a year. So let's see what that is. So t is going to be 730. Alright. Now we need to set up an equation. So we can set it up using the half-life model or the relative decay model. I'm going to set up with the relative decay. So we have m is equal to 500 times e to the negative r times 730. We are asked what is m, and we need to find what is r. So to find r, what we need to do is keep in mind this information right here. Can't really see the yellow, or at least I can't see the yellow. We'll use this green one. Yeah, we can see that better. So we'll indicate that we're going to do our work over here. So if h is equal to 140, then we can use our equation here, where natural log of 2 over 140 is equal to r. So first thing I'm going to do is prep my calculator. Natural log 2 divided by 140, store that in there. So I have my r value stored in my calculator. So then now we can do our calculation. So m is going to equal 500 e to the negative natural log 2 over 140 times 730. So we have 500 times e to the negative natural log 2 divided by 140 times 730. And we get 13. Alright. So it's not sticking around for very long. Within 2 years it's decayed to 13 grams. So mass will equal 13, let's say 13.5 grams. Alright, our second question. How long will it take to decay to 100 grams? Well, we know from our first answer that it has to be less than 2 years. Otherwise we made a serious error somewhere. So let's go ahead and figure this out. So number 2. So we're asked how long will it take for it to decay. That means we are looking for time. So this here tells us that we are looking for time. And I guess we'll use another color now. This right here is a value for m. So m is going to equal 100. So what we have then is 100 is equal to 500 e to the negative natural log of 2 over 140, and we said that t is unknown. So we can divide the 500 over. So we'll just divide 500, 5 by 500. 1/5 is equal to e to the negative natural log 2 over 140 t. Now we need to take a natural log of both sides. So we have natural log of 1/5 is equal to negative natural log 2. Oh, whoops. I missed it. I did a step in my head by accident. It's equal to natural log of e to the negative natural log 2 over 140 t. Alright. And then we can cite our property where these two will kill each other off, leaving you with natural log of 1/5 equaling negative natural log 2 over 140, all that times t. Alright, so I'm going to divide out our negative natural log 2 over 140. That's the same thing as multiplying by 140 over negative natural log t, or negative natural log 2. So then t will equal natural log of 1/5 over, well, we need our 140, so there's times 140 over negative natural log 2. Now, sometimes a student of mine will be worried because they see a negative here and think this quantity is negative, when in reality it's actually positive, because if we recall, natural log of 1/5 is the same thing as natural log of 1 minus natural log of 5, which is going to equal negative natural log of 5, because natural log of 1 is 0. So we could actually simplify this as, well, so then since we have a negative here and a negative in the numerator, negatives cancel out. So we just have natural log of 5 times 140 over natural log of 2. Let's figure out what this value is. So natural log of 5 divided by natural log of 2, I forgot my 2 in there, times 140. Alright, so if we remember, t is in days, so this is t is equal to approximately 325.1 days. So we do not want to use equal signs here. So this right here, we do not want to use equal signs. We want to use this instead, because it signifies that it's approximately, it's not exactly equal to. So right here in pink, I had the equal sign because that is exactly what it equals, but when we convert to decimal, we chopped off the infinite number of decimals, so that's why it's approximate. Now, one thing I do need to note now, I have seen students who look at this natural log thing here, and then they think, oh, hey, I can cancel out those natural logs and get 5 times 140 over 2. We have a word for this in mathematics. It's a very precise technical term, and it is called mathematical heresy. You cannot cancel out the natural logs, so you need to have the natural logs there. It would be heresy if you just thought you can cancel out those natural logs and do that. So never ever do this. That is bad, 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 bad. Never commit mathematical heresy. Alright, let's keep scribbling that out because that is bad. So keep that in mind. You can't just cancel out natural logs on a whim like that. Alright, so if you've enjoyed this video, please consider subscribing to our channel. We will continue our investigation of applications. So by now you're probably wondering, how many applications are there? And the answer is quite a bit, actually. It's very, exponentials are very useful. Again, if you like our content, please consider subscribing and check out our Patreon page. Thank you for joining our math party, and see you next time.